We discussed the nuclear decays in the past couple of lectures. Today, we will discuss the nuclear reactions. If we send alpha particles to gold nuclei, for example, this alpha particles will see or feel the nuclear potential of the gold nucleus when it is sufficiently near the nucleus, and it will scatter off. So, this is an experiment which you are familiar with, I believe, the Rutherford's alpha scattering experiment. The Rutherford's experiments by alpha particle using alpha particles on gold foil and other elements reveal the fact that nucleus is actually, or the positive charge particles are concentrated in the nucleus of the atom, and various other properties of this nucleus was also understood by such scattering experiments. In general, you can actually consider some A projectile sent to some target material, let me call that X, or the nucleus of the target as X, and in general you can expect that the nuclear reaction is slightly more than what is said above with the case of alpha and AU. It can actually change the nucleus itself, and it could emit. Usually there is something which is emitted, a light particle which will come out, and which will be in general different from A. So, in such reactions, nucleus or the original nucleus is transformed X is transformed to a new nucleus Y. Now, how do we actually understand the properties of this, or what are the ways that we can understand this? To start with, let us look at the basics of scattering process itself. To simplify matters, we will consider first a classical hard ball scattering, by which what I mean is the following. If you have a hard sphere, take a steel or iron sphere, right. So, this is your iron ball, and now let us send some smaller beads or balls onto this. What will happen? If you send, so let me draw a line which actually will pass through the center of this ball, and if I send a bead along the line joining the bead and the center. So, the momentum is directed towards the center of the sphere. Then what will happen? It will go, I mean, this is simple classical scattering. So, it will go meet the hard ball, and the norma is perpendicular to the tangent at that point, and then that is along the motion of the normal at the point where the bead meets the hard sphere is along the momentum of the bead, and therefore, it will actually turn around. So, let me don't confuse you by drawing it in a separate position. So, it will actually go back. Maybe what I will do is to actually use different line, different color. So, this, let us assume that it is actually a straight line. So, now you have a bead. The red bead is the one which is bouncing back from the hard sphere. Okay. Now, if you instead take this original bead and then send it away from, or send it in such a way that the momentum is not now directed towards the center. If you take the momentum direction and a line passing parallel to that momentum direction, but passing through the center, and then there is a small gap, let me call that as B. Okay. So, this is just the distance between the line passing through the center parallel to the direction of motion of the bead and the direction or the line, the perpendicular distance of the bead from that particular line. So, then what will happen is the point where the bead meets the ball, the normal to that, which is basically the line joining that point and the center for a sphere, is the normal. So, there is an angle between the momentum direction and the normal, and therefore, it will actually reflect or bombard this hard sphere and come out not in the same or opposite to the direction as in the case of, as in the earlier case, but will go at some angle, making an angle with the earlier this one. So, this will be the one which goes out. So, the red ones are the ones which actually are coming out after the scattering. Now, let us say we consider some other point, take B to be larger and then B to be equal to, so let us say this is R. So, B is equal to R case. So, in this case B is equal to R, which is the radius of the sphere. In that case, it just grazes, right, and pass unscattered. So, it will, the scattered one is basically not scattered, it moves on in the same direction. So, now this is what usually happens in the case of hard ball scattering. So, depending on what the position, what is the direction of the momentum and the initial conditions, the ball will scatter in different directions. All right. So, now let us say we take beads coming out. Initially, let us send a beam of these beads. A lot of these beads are put in some particular beam in a particular constrained direction. All of them are going in the same direction with the same momentum or slightly different momenta, but let us consider it to be the same momenta, say, and they are all going in the same this one, but they are all not at the same B value. So, B, that B value is called the impact parameter. So, the impact parameter for different particles in the beam could be different. So, let us take such a this one, and if I consider a small section of that beam denoted by this dB. Now, I am not indicating the individual balls, but many small balls are there in this blue band, and you see that they will reflect as a result of scattering and then come out at some angles, and the angle with which this will come out, all these particles beads inside this small band differing by. So, let us again denote the parameter, impact parameter as B, and the small width of this band as dB. Then we will see that they will come out at some angle, and if I keep my detector D at this position, I will receive all these things if the detector is sufficiently large in that way. Essentially, the idea that I want to convey is that depending on the impact parameter, the beads will scatter in with different angles, and if you consider some small band of these beam of beads, they after scattering will go into a particular cone, and if you put a detector in that cone, in the interfering that or in the put in the way of the cone, then you will receive all these ones. And if you change the impact parameter, certainly the scattering cone's angle will be different, firstly. Secondly, the position of that will also be different. So, these position of this etcetera will depend on what is the impact parameter etcetera. Not only that, if you take a different sphere, the scattering sphere, the big sphere with a different radius r1 instead of r some r prime or 2r or r by 2, then you will see immediately, you can draw that again, I do not want to draw it again, but you can do that yourself, and then you will see immediately that the angle of scattering and the cone angle, the width of the cone etcetera will depend on the size of the. So, supposing somebody hides this area from you, okay, they put some kind of a screen in front of you, right. So, something like a green screen like this, okay, and put it so that it will cover your scattering point object, that is the big sphere, and you send this beam of small beads and you put your detector D there and you receive this D from this one. In fact, if you do change the detector around and then find out how many particles are coming at different angles etcetera, you may be able to reconstruct scattering sphere, okay? Roughly. Some idea about the scattering sphere you will be able to obtain without actually looking at the scattering sphere, but by observing the scattered particles or beads detected by your detector D. So, this is something which is applicable in a very similar fashion in the case of quantum mechanics and especially in the case of nuclear scatterings. We will come to that. But before that, let me define something what is called a very useful and important quantity called the scattering cross section. What is that? Let us again take that hard sphere scattering. So, we already mentioned told this, but if we take some small area of cross section. So, let us consider some small part of the beam with impact parameter P for the inner side of the band and outer side it is B plus dB. So, the thickness of the band is dB, and then you will expect that you will get the scattering, this will scatter into some kind of an angle, which let me denote in this fashion, and then it will, if you put a detector there, you will able to see these particles there, correct. And now, a small cross section here, let me consider a small cross sectional area. There is a, if you take cross section or the area of this beam or section of the beam perpendicular to the beam itself or the direction of the momentum and denote it by d sigma. So, d sigma is some small area there, okay, of cross section, which means it is perpendicular to the direction of the motion, which is in this particular case geometrically it is equal to B dB d phi, where phi is the azimuthal angle. I do not want to complicate the diagram by drawing this, but I hope you understand what is the azimuthal angle. It is the angle as you go around the beam, that you make as you go around the. Now, let us say you have a beam, the flux of particles in the beam or the beads in the beam, let me denote it by F. Basically, that is defined as the number of particles per unit area or passing unit cross sectional area of cross section perpendicular to the area of cross section, means it is the area perpendicular to the beam direction in unit time. So, let me explicitly write that so as not to confuse you, perpendicular to the direction of the beam. In unit time. That is basically what we call the flux. So, just remember that F in our discussion today denotes the number of particles or the beads in that is passing through a particular through unit area perpendicular to the direction of the beam in unit time. So, if I multiply d sigma by F, the flux, and that will give me will be equal to the number of particles passing through cross sectional area d sigma, right, in unit time. Now, that is equal to F d sigma, and in the hardball scattering case, all of these particles, as you can see, will scatter into the detector there, and this is the these particles are detected by the detector D in figure. Just refer to the figure, right. Let us say the position of the figure kept at r theta phi. Okay. So, in polar coordinates r theta phi is the position of the detector. Now, if you are clever enough and then if you look at the figure closely, then you will say that look if I extend this cone, then actually the position, or if I look at the cone and the detector's position, the r theta phi is not really the kind of thing that is the distance from the center of the sphere. It is the definition of this r theta etcetera, you can actually have from either the point P or from O, right. So, the way we have actually discussed, it is actually from the point P that we have to discuss this r theta phi, but in a practical case what happens is that the detector is kept far away from the scattering center, far away in the sense that at large distance compared to the size of the sphere itself. In a classical scattering, we can take a football size sphere and keep a detector close to it also, say in very close to the surface itself. or something like 50 centimeters from the surface. That is not very far compared to a large distance compared to the size of the sphere or the scattering object. But in the case of nuclear scattering, think about Rutherford scattering, what is happening is there is an alpha particle which is sent as the projectile. So, your beam of these beads will be replaced by the beam of alpha particles, and you have a scattering object as the nucleus as the scattering object, nucleus of gold or some other material as the scattering object, which is the extension of that is just some kind of order of Fermi's, 10 power minus 15 meters. Where do you keep the detector? Detector is usually kept slightly far from this foil, say at least half a meter or 1 meter like that. So, 1 meter is very large, 10 power 15 times large compared to a Fermi, a few Fermi. So, that kind of distances are much very large. So, for those or practical purposes in such cases, we can actually think about scattering in potential to be very small point like that, and you have your detector kept at some point somewhere here D, and this angle theta and say azimuthal angle we consider it as phi and a distance r. So, this can be measured from the scattering point, or in the case of the hard sphere scattering from the center of the sphere. So, we will not distinguish, we will not make that difference between those two are going to be very small. So, we will not worry about that. Now, that we have actually defined this, identified that in such cases particles passing through d sigma cross section is going to go to a detector which is kept at some distance r at an angle theta at an azimuthal angle phi. Okay. Now, so this is theta and phi, let me denote it that way, and then you have the detector here. Your detector has some area of cross section, let me denote the area of cross section of the detector as dA, and A, not A, R is the distance of the detector at from the scattering center. This detector is a 3-dimensional object, and then that makes an angle what is called a solid angle, okay. Solid angle, let us denote it by d sigma d omega, which is defined as dA divided by r square. It is like this, you take the section of the sphere as approximate the area dA as part of a sphere with center O, the scattering point, and distance or radius r. Okay. If dA is the area and then r square is the r is the distance or the radius of that sphere, then dA itself approximate part of sphere or as part of a sphere, dA is equal to r square dr d sin theta d theta d phi. So, solid angle d omega is dA is r square, dA is equal to r square sin theta d theta d phi. So, d omega, the solid angle, is dA over r square, which is essentially sin theta d theta d phi. Now, therefore, suppose for convenience I consider r theta phi as the rate of particle scattered into the detector. So, imagine, let me say that again, we have a beam of these particles sent to the scattering point, and now you keep a detector at r theta phi, and you ask the question how many particles are being detected by this detector in unit time. So, that is the number of particles scattered into the detector or the rate of the particles scattered into the detector. All right. So, this in another way, r theta phi is the number of particles scattered by the scattering sender. In the case of hard sphere scattering, the scattering center is basically the sphere, hard sphere. Scattering sender to an angle, to polar angle theta, and azimuthal angle phi, polar angle. So, r theta phi is the number of particles scattered by the scattering center at polar angle theta and azimuthal angle phi in unit time. So, that is basically the rate. In another way, r theta phi is equal to number of particles scattered into unit solid angle around theta phi. Fine. Now, we can ask the question, what is the rate of particles which are received into angle d omega? The d omega, let us say, is the solid angle defined by the detector. Okay. So, the number of particles scattered into the detector, let me call it as detector with solid angle d omega. What I mean here is that the detector, when it is placed there, it has some area of cross section, okay, and that area you divide by the r square, the distance square of the distance of the detector from the scattering potential. That is going to be r theta phi, which is basically the number of particles scattered into unit solid angle, right. This is equal to r theta phi times d omega. That is a straightforward thing to understand. Now, we already said that if we consider some small d omega, d sigma area, cross sectional area in the beam, and f as the flux, then this number is equal to f d sigma. So, we have f d sigma equal to d omega times r theta phi, or I can have a quantity which is called d omega over d sigma over d omega as r theta phi over f, where f, remember, is the flux. This quantity is called the differential cross section, scattering cross section. Okay. Again, let us see what is the physical significance of this. If you do not know what is the object that is scattering this, suppose let us now let us replace this hard sphere with some kind of a hard surface of object with hard surface made of metal, some metal say, but with some oblique or arbitrary shape or slightly deformed shape, and we do not know what the shape is. And we send these particles and then look at the scattered particles all around this scattered object, and it is expected that we will be then able to get some idea about the scattered particle, the scattering particle, okay, by looking at, by observing the pattern of the scattering. So, d sigma over d omega will give you some idea about what kind of object, the scattering particle object is there, sitting there and scattering it. And you can easily compute this d sigma over d omega, not by looking at the beam and beam the cross section area, etc., measuring the cross section area in the beam, but just by looking at the rate of particles which are detected at a detector, kept at in a detector, kept at solid angle, kept at angle theta phi, which having a solid angle cross section d omega, and knowing the initial flux. So, this is what idea is, and it is actually a very useful thing to understand the scattered potentials in the case of nuclear scattering as well as any other quantum mechanical scattering, particle scatterings included, elementary particle scatterings included. So, what we do now is so we got some idea of what is the scattering and what are the things that is relevant there, and then a particular object called particular quantity called cross section or differential scattering cross section. We will take these ideas into the quantum mechanical system, a nuclear scattering, say alpha particle and gold nucleus, or any other neutron object and then some other nucleus, a neutron as the projectile and then some other nucleus as the target, for example. In whatever the system is, the nuclear system that we are considering is, let us say that this kind of ideas can be adapted there. So, what is the situation there? In a quantum mechanical process, you cannot actually think about path of the particle like the bead, the impact parameter, etc. Quantum mechanical process systems has its own uncertainty with this in position measurement and momentum measurements. So, various things are not very well defined. Well, they are defined, but they cannot be precisely measured. So, therefore, we cannot actually define quantities based on particular momentum and particular distance, etc. in quantum mechanical systems. But still, we can send the neutrons, we can prepare beam of neutrons, we can prepare beam of alpha particles, we can send them to target nuclei like gold nucleus, and we can keep our detector around this at various different positions of choices, and we will be able to detect these particles, and then we will be able to tell how many of these alpha particles are received by these detectors. Detectors are capable of doing even more, but let us limit our for the discussion, let us consider only the number of particles which are detected by the detector. This can be done. So, we can actually define a similar quantity d sigma over d omega that we just now discussed and defined. And another thing is that the nuclear potential itself, it is not a hard sphere potential that we are considering. So, in nuclear scatterings, we have no bead like classical bead like projectiles. What I mean by projectile is the beam of particles which are sent to the target. Okay. And the scattering center is somewhat unlike the hard sphere. A hard sphere has a sharp boundary etc. But whereas in the case of nuclear potentials, you know that although the nuclear potential is confined to small regions, it is short range potential. We saw that it is actually not something which actually falls down suddenly to 0. It is at the boundary, it is hazy, it is gradually going to go down to 0. So, there are differences, but even in those cases and then what we do is basically we send not the beads like particles, but quantum particles towards the scattering potential. But in such cases also still we can define the distribution differential scattering cross section d sigma over d omega, which is equal to r theta phi, the rate of particles detected by rate of particles falling into unit solid angle around theta and phi divided by f. Actually, in the case of Rutherford scattering, if you consider Rutherford scattering, you cannot keep one particular nucleus as your target. What you do is to take gold foil and keep it there, and gold foil has many nuclei, not just one single nuclei. So, the scattering of alpha particle is not by a particular single nucleus, but by some number of nuclei there. So, the number of particles which are scattered into a particular angle will depend now on what is the number of particles or the number density of the particles, the target particles also. So, we have to consider that as well, and then we will along with the flux of the beam, we will have to consider the number density, where n is the number density of target and f is the flux, r is what we have just now defined, and then that will give you d sigma over d n. N can be computed. We know the number density of nucleus in a gold foil or any other target that we will consider in a particular scattering. F is what we are preparing, the number of alpha particles etc., or the flux of the alpha particle or the neutron, and r is what we are detecting. Okay. So, in principle all these things can be are computed, and therefore, d sigma over d omega can be computed. This is now a computation of this d sigma over d omega from observed and prepared initial quantities and the observed quantities, and that should give, as we discussed, some idea about what is the scattering potential, what the properties of the scattering potential, and that is precisely the idea of this scattering experiment. Through the scattering experiment, we will be able to actually understand what kind of potential that we have, what are the interactions that the projectile will have with the target. All right. If we, so we have d sigma over d omega equal to r theta phi over f n, correct. Now, we can integrate this. What do you mean by integration? I mean, so mathematically you can integrate this expression, but physically what happens? Integrate d sigma over d omega to get total cross section. Right. So, when you say you integrate it, you take small such sections and add them up, right. So, that is what integration is. Integration is a continuous addition in the case of continuous variables, continuously changing variables. So, basically you take the detector in an experiment. What you can do is to take the detector, keep it at some angle, take it at some other angle, some other angle, some other position, all these positions, and add all these numbers, and then that will give you r integral of r theta phi when you cover the entire area of the spherical of the imaginary sphere with radius r, which is basically the distance of the detector from the scattering center, and center of the sphere is taken as the center of scattering center. So, now sigma is equal to integral d sigma over d omega, which is equal to r by f n into d omega. Okay. So, this is what you have to do, and that is equal to, you can actually, I will write it in terms of theta and phi d sigma over d omega into sin theta d theta d phi. So, this is the total cross section. And what is the meaning of this? This will give you the probability, sigma gives the probability of scattering to take place. So, this actually will give you the probability for emission probability of detecting particle anywhere, the total probability. It is the probability of detecting the particle anywhere in the around that scattering center. Okay. All right, there is one more small piece of this that we want to discuss, but maybe we will discuss that in the next class.